On to question 5. So without referring to a graph, we want to prove that this function g has at least one real root. So when it's asking if there's one real root, that means, well, one value of x where g of x is equal to 0. So we want to find, well, is there any values of x where anything before or after, so where that value, or the value of the function is changing sign, so either from negative to positive or positive to negative. So first thing I want to mention here, so here we have cosine of x minus x cubed. Well, cosine of x is continuous for all values of x, right? It's always going to be oscillating between -1 and +1, like between those values, right? And then negative x cubed is just a polynomial function. So g of x is continuous everywhere. So we know it's continuous, so we just need to use that to find if there's a root. And we can think about using the intermediate value theorem for this. So if we can find some interval, say x1 to x2, where the signs change, so either from negative to positive or positive to negative, for g of x, then we know there's going to be some root. So just thinking about cosine, well, cosine, if you think about the unit circle, we're along this x-axis. So let's just try these two angles here, so when x equals 0 and x equals pi. Well, we know the value of this function is defined at these points because it's continuous everywhere. So g of 0 is going to be equal to cosine of 0 minus 0 cubed. Cosine of 0 is going to be positive 1, and then we're going to get 1 minus 0, so we get 1. And notice that's positive. Next, let's try g of pi. Cosine of pi minus pi cubed. Cosine of pi is going to be negative 1, and I'll just leave the negative pi cubed there. We don't need the exact number here, we just need to know that the sign here is going to be negative. So we take a value that's negative and subtract something from that. Just going to make it more negative, right? So notice here between these two values, it's positive and negative. And on this closed interval, 0 to pi, it's defined and continuous between this interval, right? Because it's continuous everywhere. So one comment I want to make is I picked 0 and pi, but you could pick some other values that you'll find a positive and negative. Just test it with whatever you feel. If you end up getting two positive values, then you'll need to pick something else. If you get two negatives, same thing there. So we want to find two different values of x where we get that sign change. So then using the intermediate value theorem, since g is continuous everywhere, right, because we have the sum of this cosine function, which is continuous everywhere, and the polynomial, we know that g is continuous on this closed interval 0 to pi, and since we have a sign change, but within this interval, there must be a root in that closed interval. And remember, the root is just going to be that 0 or that value of x where our function g equals 0. Question 6 says, suppose that f of v represents the fuel efficiency of a car in miles per gallon, so miles per gallon is our unit there, when driving at a speed v, so v is in miles per hour. And they want us to describe the meaning of f prime of 50 equaling negative 0.74. We wanted to discuss the units. So remember, the derivative is often going to describe the change of the function, so that rate of change of the function. So now we need to think about the units. Well, our input, our v, is in miles per hour, when our output of the derivative is going to be similar to like slope formula, where if you're going to have the change in y over change in x, well, our change in y is going to be that fuel efficiency in miles per gallon over the miles per hour. So to describe what's happening here, we say the fuel efficiency of a car, well, since we're working with the derivative, it's changing at a rate of negative 0.74 miles per gallon per hour when traveling, so when you're going at a speed of 50 miles per hour. All right, so if we think about this here, for every additional mile per hour faster that we're going, it's causing the fuel efficiency to go down, since it's negative, by 0.74 miles per gallon. On to the last question of the exam review. So question 7, we're just going to be computing the derivatives of all of these different functions. So for the first part, for part A, we just want dy dx. So notice that we're given this function y, and we want to differentiate it with respect to x. Well, since x is our only variable here, we can just use the power rule all the way through. So dy dx is going to be equal to, carry down the 4, we're going to get 20x cubed. Similarly, we're going to get 33x squared, then 8x to the first power, and then that negative 8 is constant, so its derivative is going to be 0. So this is going to be our answer for our part A. Next, we have part B. So similar to part A, we're still going to be using power rule. However, let's try and rewrite this one here so that it looks like something where it's a little bit easier to take the derivative of. So I'm going to write to the side f of x is equal to pi x, and notice that pi is just a constant, just like this 11 here is. So then I'm going to rewrite that as negative x to the negative fifth. So to bring the exponent on that bottom part up to the top, so up to the numerator, we can just negate that exponent there. And from here, we can just take the derivative using power rule. So for the first part, we're just going to be left with pi, and then we're going to get minus a negative 5x to the negative 6, or pi plus 5x to the negative 6 as our answer there. All right, these last two are the trickier ones because we're going to have to use either quotient rule or product rule here. So for part C, we have one function on the numerator and another function on the denominator. So we'll need to use quotient rule for this one here. So just to recall our quotient rule, so for d dx of f over g, we're going to get f prime of g minus g prime of f over g squared. And so to simplify this just a little bit, I'm going to find what the derivative of the top and the bottom would be before we start plugging everything into this quotient rule. So I'm going to rewrite this as t squared plus t to the 1/2 plus 1, so we can use the power rule for that one. So that's going to be our numerator, that's going to be our f, and then this is our g at the bottom. So we have f and g. Now we need to find what f prime is. Well, f prime, just use the power rule, so we're going to get 2t plus 1/2 t, and then subtracting 1 from 1/2 gives us negative 1/2, and then that plus 1 is just going to be a constant, so it's going to 0. And then for g prime, again, using power rule, we're going to get 3/2 t, subtracting 1, we're going to be left with 1/2 there. So we have fg, now we have f prime and g prime, so let's just plug into our quotient rule to get our final answer. So dg dt is going to be equal to f prime, so 2t plus 1/2 t to the negative 1/2, times our g, which is t to the 3/2, minus our g prime, so 3/2 t to the 1/2, times our f, which is t squared plus t to the 1/2 plus 1, all of that over g squared. So that's going to be t to the 3/2 squared is going to be t cubed. Those halves are going to cancel out there. So we're left with t cubed on the bottom. So you could rewrite parts of these with the negatives to go down the denominator, with the roots to have the square roots, but I'm going to leave it like this. The answer will be the same. Just want to use the quotient rule there, and that'll be our derivative. And then finally for part D, we have f of x equals x e to the x over 2, and we want to find the second derivative for this one. So we want to find the first, and from the first we can find the second. So one thing to notice here, this 1/2, so this 2 on the bottom is the same as multiplying by 1/2, so I'm going to pull that out to the side here. And using product rule, we can say this is our function f and this is our function g. So remember, for product rule, it's going to be f prime times g plus g prime times f. So if our f is 1/2 x and our g is e to the x, then our f prime of x is going to be the derivative of f, so just 1/2 times our g, or e to the x, and then add, well, our g prime is going to be e to the x, so we're going to be left with that 1/2 x e to the x here. So because e to the x is its own derivative, we're going to end up getting this same term every single time we use the product rule here. And so you notice that this is the same as f of x. All right, and one more time, we're going to take the derivative because it's asking for the second derivative. So again, we'll need to use the product rule, but for this part here, 1/2 e to the x, we can take that as is. We're just going to be left with 1/2 e to the x. Using product rule again here, we're going to get that 1/2 e to the x plus 1/2 x e to the x, which is the same as f prime of x, right? Because we took that derivative initially. And we can simplify that. We can add the 1/2s together here to get just e to the x, and then leave this last term here. So our final derivative, our second derivative of the function here, is going to be e to the x plus 1/2 x e to the x. And there you go.